Thanks. Okay, so yeah, so very sorry about this long title with lot of jargon, but hopefully I'll try to communicate. So this is work done with Satyam Sinha, who is a master student at IISr and has been spending time at ICTS. Rekha Kumar, who's a postdoc at ICTS. Junaid Bhatt, a former student at ICTS, who's now in Kashmir University, and Diptiman and Shankar. Okay, so this is the problem. So we are looking at quantum, basically quantum Hall effect, and which was discovered by Klitzing in this experiment in 1980. So basically, consider a 2D sample, and with a magnetic field going into this, and let's say we apply some potential difference across these two edges. Okay, so there's a potential difference across these two edges. Okay, so there's a perpendicular magnetic field, so electrons will kind of drift because of the Lorentz force, and you get a voltage difference across this. Okay, so if you measure the voltage difference, let's call this VH, the Hall voltage, and let's say the current across this is I, then this is called the Hall resistance. Okay, so classically, if you measure this Hall resistance as a function of magnetic field, you would get a straight line. But what was discovered is that you get these funny plateaus, which are exactly quantized in units of h by e square. Okay, so this is the quantum Hall effect. Okay. Okay, so now what is the theoretical understanding? So the main observation is you look at this transverse conductivity or conductance, which I call the Hall conductance, and it's quantized in units of e square by h. Okay, so I mean, one of the first theoretical explanation was given by Laughlin in 81. And so I'll try to explain this a bit, his argument later, but it was based on gauge invariance and the existence of a gap. And then there was a paper by Halperin which kind of pointed out that edge currents are very important. So in this geometry, basically edge currents means that there's a current going across it, but it's almost localized at these edges. Okay, so this is something pointed out by Halperin. And then the connection with topology was established in this very nice paper by these people, who gave this so-called TKNN formula, where you basically consider this, let's say, this 2D sample on on a periodic geometry. So it's on a torus, and you calculate the Green-Kubo conductivity. Okay, this transverse conductivity sigma xy. And what they showed is that you can express it in terms of a topological invariant, which is a Chern number. So this is the relation. Okay, so this is basically it's an infinite system or a periodic system, and you compute the the electrical conductivity transverse, and you show that it's actually exactly related to some topological invariant. Okay, and this topological invariant can only take integer values, and so that's why it shows that this has to be quantized. Okay, so let me explain this, what this invariant is a bit. Okay, so if you have a let's say two-dimensional lattice with periodic boundary conditions, you can form block states. These states, so you get various bands which are labeled by n, and there's some momentum kx, ky, right, where these are in some Brillouin zone. And you can construct this so-called Berry potential. So given these wave functions, you can just construct this vector. And then you can take a curl and compute this Berry curvature. Okay, so if you integrate this quantity, so you just need the eigenstates, and you can then compute this quantity. And if you compute it over the Brillouin zone, just the integral, then you get some number which you can show it's exactly quantized. Okay, it can only be an integer. And what TKNN showed is that they related this to the conductance or conductivity. Okay, so now let me come to this Laughlin's argument. So he considered a cylindrical kind of geometry, and so this quantum Hall system is on a cylinder, and you apply so it's like a ribbon where you apply a small voltage difference across these two edges of the ribbon, right? And then again there's a magnetic field passing perpendicular to this ribbon, and so this will generate a current in this direction. And what he showed in this paper argued that if you take delta V by I, that's exactly quantized. Okay, so the main ideas in his proof are based on gauge invariance and something called a Byers-Young formula. And he also showed why So when you take this sample and you connect it to leads, right, you have to apply this voltage difference, you have to put leads. So you have to argue why this lead system coupling can be neglected, and this is something he did. Okay, so this is Laflin's proof, and then, oh really? Okay, and then there was a paper by Halperin which argued why the importance of edge states. So in this geometry, you have two bands, and then you have these edge modes which are localized exactly at the edges of the cylinder. Okay, and this actually contribute to the Hall conductance. Okay, so in this work, what we do is we do a microscopic computation of this geometry, this Laflin geometry, and so you consider the system connected to leads and so on, and the main question is, like once you take into account these leads and coupling and so on, is this Hall conductance still quantized, and can we identify a topological invariant, right? Like now the states are completely different because you have to compute the scattering states, and so this is the question. Okay, so this is the geometry. We have the Chern insulator, which was the usual cylinder, but now you attach leads, okay, and then you want to understand the states and the conductance in this system. Okay, so first of all, you can, because of this cylindrical geometry, you can easily go to do a Fourier transform in this y direction, and you can compute so it becomes essentially like 1D system, and you can compute the scattering states. So the states basically look like there's an incident wave and there's a reflected wave in the lead, while in the insulator, there's just a decaying wave function. Okay, so this is the spectrum in the gap of the insulator. Okay, so of course, because it's an insulator, you can't have transmission, so you have decaying modes inside and wave going in and reflected. Okay, so in particular, you have a reflection coefficient, and because there's no transmission, it's a pure phase, so you write it as e to the I chi. Okay, so this one can obtain an explicit solution, and then you can, given the wave function, you can compute the currents in the y direction, which is what we want. And so you can compute the currents explicitly. So in the Chern insulator, it's decaying exponentially, while in the leads, it's some oscillating function. Okay, then you have to integrate this current over the over the Fermi surface, and so you can do this integral. And supposing you now look at the current, this y current in the entire sample, just let's say you have to do some numerics and you look at the current. Okay, so what's very interesting is that you find that apart from the current inside the insulator, you also get a current in the lead. So this is what we call the proximity effect. Okay, so the insulator has time reversal breaks time reversal invariance, so you can have chiral modes, but it also kind of induces a current in the leads. Okay, so we can show that these currents have some either power law or exponential form depending on the lead parameters. And then we can compute the total Hall conductance, and we show that it's actually related, you can relate it to a winding number, and you can also relate it to a Berry phase. Okay, so, and then one of the surprising things is that we find that this winding number is for some parameter regimes, the winding number is non-zero whenever the Chern number is non-zero. But in some other parameter regimes, this is not true. Okay, so you can have a finite Chern number, but the conductance can vanish. Okay, so I'll stop here. Thanks.
Questions?
Yeah.
So, what is the value of the coupling between the lead and the insulator compared to the bulk gap of the insulator?
Okay, so see, I mean, what we show is that these are the parameters in the leads, and for example, in this parameter regime for any coupling, you get quantization, while in this parameter there is a certain range of coupling for which you get quantization. So, but I mean, there's no limit on the couplings. It's not like weak coupling or. Okay, so everything is kind of measured in units of the system. Yeah, it can be anything. I mean, so everything is measured in units of the system hopping.
So, Abhishek, what are the integer values that C can take? I mean,
see, in the model that we look at, it's the spinless BHZ model. It can only be 0, +1, +1, and -1.
Okay.
Right. Yeah. Okay.
In the interest of time, we won't take further questions. Let's thank the speaker.